In question 4a, we need to define tensile strain. Well, this is defined as the change in length divided by the original length. In B, we need to refer to figure 4, which is a stress-strain graph for a copper wire, to state the breaking stress of the copper wire. Well, reading from the graph, this is at 1.9 times 10 to the 8 pascals. In C, we need to mark on the diagram a point on the line where we consider plastic deformation may start. We need to label this point A. Well, this starts beyond where the line is no longer straight, at around 1.5 times 10 to the minus 3. In D, we need to use the graph to find the Young modulus of copper, stating an appropriate unit. Well, Young modulus equals stress over strain. This is the gradient of the straight part of the graph. Putting in values from this, using as big a triangle as possible, gives a value of 1.2 times 10 to the 11 pascals. In E, the area under the line in a stress-strain graph represents the work done per unit volume to stretch the wire. In part 1, we need to use the graph to find the work done per unit volume in stretching this wire to a strain of 3.0 times 10 to the minus 3. Well, we need to show that we've counted the squares on the graph. I got around 38 squares. Each square has an area representing 0.2 times 10 to the 8 pascals times 0.5 times 10 to the minus 3. This is 10,000 joules per cubic meter. So the total work done per unit volume is 38 squares, each at 10,000 joules per cubic meter, giving 3.8 times 10 to the 5 joules per cubic meter. In part 2, we need to find the work done to stretch a 0.015 kilogram sample to a strain of 3.0 times 10 to the minus 3, given the density of copper at 8960 kilograms per cubic meter. Well, volume is mass over density, and work done will be work done per unit volume times the volume. So, we need our work done per unit volume found previously times the density. So, we need the work done per unit volume found previously multiplied by our expression for the volume. Putting in the other values gives an answer of 0.64 joules. In F, we have a certain material with a Young modulus greater than copper undergoing brittle fracture at 176 megapascals. We need to draw a line onto figure 4, which I've represented here, showing the possible variation of stress with strain for this material. Well, with a greater Young modulus, it will have a greater gradient, and it will also stop rapidly with little or no bending at 1.76 times 10 to the 8 pascals, which is 176 megapascals.